had a chance to sleep in a little bit? A little bit, maybe, yes. Good. So, before we get started, excuse me, a couple just housekeeping kind of things. We're doing really well on the Moodle registration. I only have about 50 people that still need to register for the exam. At this point, that means you're going to be taking session 3, starting the exam at about 9 o'clock Thursday night. That's the only session that's open. But please do make sure that you are registered for the exam. If you're not registered, you're not taking the exam. All right? Keep that in mind. If you do have a conflict with the exam, I think hopefully most everyone has been in touch with me. You need to get that resolved with me today. Okay? And then once you have my permission via email, then you can sign up for the exam conflict on Moodle. Right? But you need to have an email from me saying that it is okay to register for an exam conflict in order to do that. And those people with disability service accommodations, please make sure that you sign up over with disability services. They've got their clockwork program for that. You'll be taking the exam over with them. So please make sure that gets squared away. And again, that really needs to get done today. I know they like to have that done 7 days in advance, but if you haven't done it and you go do it today, and they give you a little trouble, have them call me, and I will I'll help you out with that. So just make sure that gets done today. Get that all squared away. All right. So any questions with that kind of stuff? We have the SIs are going to run the review for the exam on Monday night. Right? So that's going to replace the typical Monday SI session. It's going to be in here a little bit longer. So they'll be answering your questions and going through all the material for the exam. The practice exam will be going live. It'll be on OWL tonight at about 6 o'clock. Right? There's 3 different versions of the practice exam. They're all the exact same questions. So it's just 3 different opportunities to take the practice exam. The first version is just a simple list of questions that you'll go through. So it looks very much like a standard OWL assignment. So it's just a chance to practice some of the material. Then there's 2 other practice exams. One is listed as timed and the other is untimed. Those are in the exact same format as you'll see when you take the exam. It's the exam testing format is what we call it. The untimed is obviously untimed, so you have as much time as you'd like to do that. And then the timed version, you'll have 65 minutes to complete that exam. So once you open up that practice exam, you have 65 minutes to finish it. There is some feedback built in to the questions. When the untimed version of the practice exam, unfortunately, the way the software is written, you're not going to see the feedback with that. All right, we can't do that, but you will see the feedback with the timed version of the practice exam. You just have to wait for that 65 minutes to elapse. So if you finish the practice exam in half an hour, the feedback's not going to be immediately available. Give it another 35 minutes, then come back to it, and then you'll see the feedback to the question. So if you did get them wrong, it'll either lead you, point you to the appropriate section in the OWL book, or if it's a mathematical problem, it'll run through the steps of math to solve the problem. And so it'll point you in the right direction on how to solve the problem correctly. All right. Anybody have any questions with any of that? Yes. No, that's going to be on Monday. Because of the snow day. I was hoping to get everything finished today, but we'll finish up the exam 1 material on Monday. It's going to be all of chapter 14. And we're going to go chapters 15, sections 1, 2, and 3. Chapter 15.4 is not going to be on the first exam. We've had to drop that because of the snow day. All the appropriate homework is going to be due on Sunday for the exam, so you'll have a chance to practice all the problems. We'll finish up the material, like I said, on Monday, and then the class on Wednesday will not be on the exam. Right. So I'm not gonna hit you with material the day before the exam. That's not cool. Any questions at all? All right, we'll get into the stuff for today. So we're talking about equilibrium constants and just some basic background material on equilibrium constant, how to set it up. Looking at our example of hydrogen and iodine reacting together, the form 2HI showing two different situations when K is either greater than 1 or less than 1. Right? And that's going to indicate whether we have a product favored or a reactant favored equilibrium. Right? So in the case with the green line, that's talking about products, the concentration of products. So that's going to increase until equilibrium is reached. So obviously when the reaction starts, we don't have any products in the reaction mixture, so that concentration starts off as 0. And as the reaction progresses, that concentration increases until it levels off. And as soon as it hits that plateau, that's equilibrium. And the same thing is going to happen to the reactants. That concentration starts at some value, we have some amount of reactants, and that's going to decrease until equilibrium is reached. And again, that plateau is a stable concentration. The reaction hasn't stopped. We're still forming products, and we're still reforming reactants. The reaction is still ongoing. Equilibrium is a dynamic process, so it's always going, never comes to an end. But our concentrations are not changing. So at equilibrium, concentration of products and reactants do not change. They're not the same, so the value of the concentrations aren't the same. They can be different concentration values, different amounts. So that, but those numbers, what those amounts are not changing anymore. They stay constant. All right, when we're doing calculations with the equilibrium, it's really easy to get sidetracked with the information, get things in place. We want to try to keep it organized for you. And this ICE table allows you to do that. This is a great little method for organizing the information as far as equilibrium. You're going to be using ICE tables for the rest of the semester, pretty much. Right? So you guys are going to get very, very good at this. And the ICE simply stands for initial concentration, change in concentration, and equilibrium concentration. So there's 3 sets of values. What we're starting with, what's happening to the concentration, and what that concentration is once equilibrium is established. Once we hit that plateau. Using our example that we've been doing, hydrogen and iodine reacting to form 2 molecules of HI. A simple question could be, what is the equilibrium constant, KEQ, if my initial concentration of H2 and I2 is 0.0175 moles per liter. And notice the concentration bracket has a subscript I after it. That's telling you this is the initial concentration. Right. And then the question also gives you, and at equilibrium, the concentrations for H2 and I2 are 0.0037 moles per liter. And what we're going to be looking for is, we'll need to find HI at equilibrium, and we'll need to determine what the equilibrium constant is. So the ICE table gets set up. We have our initial, our change, and our equilibrium concentrations on the left side. And up top, I'm just going to put down my reactants and products. So I have my H2, I2, and HI. One thing that I also like to do, just to keep things fresh and right in front of me, I'll bring the coefficients down into the headers of the table as well. So the coefficients for hydrogen and iodine are both 1, and the coefficient for the HI is 2. Just to make sure I don't forget about that. So keep that right in front of me. So I can fill in some information here. I know what my initial concentrations are for H2 and I2. And I also also know what my initial concentration of HI is. It's 0. The reaction starts. When the reaction starts, there's no product present. Right? I know what that is. And I know what my equilibrium concentrations for H2 and I2 are. So I can fill that in. So now I need to figure out the other data for the table. And at this point, this is relatively simple because I have an initial and I have my equilibrium concentration. Doesn't matter which one I use, either hydrogen or iodine. So the change in concentration is just going to be the difference of those two values. So the change in concentration is going to be simply final minus initial. 0.0037 minus 0.0175. That math just simply works out to be negative 0.0134. Right. The reactants are going to have a negative value because I'm using up reactant. My concentration is decreasing. So the value for the change has to be negative. I'm not gaining in concentration with reactants. I'm losing concentration. Because the stoichiometry between hydrogen and iodine is the same, they're both 1, that's going to be the exact same value for the change for iodine, negative 0.0134. Now for the product, that's going to be a positive value. I'm going to increase my concentration. So I'm going to write that as a positive value. And this is also where I need to take into account the coefficients and the difference in coefficients. Simply, it's a factor of 2 different. I put a 2 in front. And I get that 2 because of my coefficient. I bring that down. That ends up being my change in here, ends up being a positive 0.0276, thereabouts. So my equilibrium concentration, 0.0276. Right? So now I figured out my HI. So now I've completed the table. Now it's going to be a relatively simple matter of determining my equilibrium constant. So from my equation, I know my equilibrium expression is going to be K equals products over reactants my coefficients from the reaction become my exponents. So I have a square term on the HI. Again, the coefficients for hydrogen and iodine are 1, so no coefficient necessary there. I always want to make sure that I'm using my equilibrium concentrations here, not my initial. I always want to use the equilibrium concentration. So I'll just plug in my values. 0.0276 squared and 0.0037. Simple math at this point. K equals 56. Don't worry, there are never any units with an equilibrium constant. It's a unitless value. One of the few times in chemistry you don't need to worry about having a unit there. Okay? It's just going to be a number. Any questions with this? Yes? Capital K. Equilibrium is always going to be capital K. Actually, from this point forward in the semester, when I write K, it's always going to be capital. Anybody else? All right. So when we're writing our equilibrium expressions, there's 2 things we never include in the expression: solids or pure liquids. And generally, this is going to be, in our cases, water. It's really the only pure liquid that we're gonna deal with this semester. We don't include the solids because the concentration of the solid is actually going to be dependent on its density, which is a fixed value. And this essentially means that the concentration of a solid is a constant. I'm not going to really get into the details of that. You don't need to spend the time on that. But just always assume that if you see a solid, either as a reactant or a product, treat that as a constant, and it does not get added in to the reaction, or to your expression. Liquids, something like water, when it's in a liquid state, so you need to make sure you check your label, because if you see H2O with a G after it, if you have gaseous H2O, that absolutely does get included into your equilibrium expression. So don't just always assume you're going to ignore water. You got to check the label to see what phase state it's in. If it's liquid, then we ignore it. If it's gaseous, we include it. So the concentration of a solvent, of liquid water, is going to be very, very high. And it's about 55.5 moles per liter is your concentration of pure water. And when you have a solvent in it, that's taking part in a reaction, it's going to actually appear as a reactant and as a product. So therefore, in your equilibrium expression, it would be in the numerator and the denominator. And the change in concentration that we'd actually be seeing in the reaction would be tiny. The change would typically be in the second or third decimal place. And you see if you divide this number and there's only a change in the hundredths or thousandths place, it's really going to still equal out to be 1. So it's going to cancel itself out. And that's why we don't include solvents in our equilibrium expressions. They essentially cancel out. They'd appear as reactants and as products in the expression. Just as a quick example, so for this, solid sulfur and oxygen react to form SO2. That's the gaseous state. So my K would simply be the SO2 over the oxygen. And that's it. And solid sulfur gets dropped. Now this K, what information does this tell us? I mentioned this earlier already, that the value of K tells us whether we're a product favor or reactant favor. So which side of the reaction is going to have a higher concentration, whether it's from product or reactant. So the greater the value of K, the more products are favored. So what this means is if my K is greater than 1, I'm going to favor my products. So the reaction is going to proceed to such an extent that most of the reactants are used up and have been converted to products. If my K is less than 1, the opposite is true. Most of my reactants are still going to be present, and I'm only going to form a small amount of products. So the reactants are going to be favored. And if my K value is about 1, I don't know. It's indeterminate. There's a balance between reactants and products. There's not a significant difference in the concentration. And by about 1, that's something, you know, the 0.1 to 10 range, somewhere in there. see something with a K value where it's e to the 4, that's obviously product based. Same thing as if you have a K value e to the minus 3, minus 4. At some point we're going to see K values e to the minus 20. Right? Those are going to be extremely reactant based. And in the two diagrams here, the one on the left, where products, the concentration of products is higher, is greater than reactants. This is an instance where K is greater than 1. And when the reactant concentration is greater than the products, this is K less than 1. This is going to be one of those things that you're going to need to memorize. It's going to make your life easier for the rest of the semester if you can just look at a K value and know whether it's something product favored or reactant favored. Right? Just keep that in mind as you're studying to make sure that you know these three factors. Right? Any questions as we go along?
What's the third row?
It is about 1. So let's get into a little bit more into the math, using the ICE tables and doing some calculations. All right? And these are going to be some typical exam type problems. So if you're good with the math, good with the process involved in these, you're probably in good shape for Thursday. So we have this molecule. This is a benzene. It's a big organic molecule. So don't worry about this C6H10I2, what it looks like. Just think of that as your reactant. That's going to react to form C6H10, the gas, and some iodine gas. So if I know my initial concentration of my reactant is 0.05 moles per liter, and my equilibrium concentration of I2 is 0.035 moles per liter. I want to find K. That's what we're going to look for. So I'll just fill in the ICE table. So we have our reactant. And we have our products. This one's nice and simple. All my coefficients are 1. That makes life easy. I like that. I know my initial concentration of my reactant. And my concentration of products is 0. And I know my equilibrium concentration of I2. Well, that makes the change in concentration in I2 pretty obvious. Final minus initial, I end up with a change of positive 0.035. It's a product, so again, the change in concentration must be positive. And because all my coefficients are 1, I'm going to use that same value for my other two constituents. So for the other product, it's going to be the same number. And for the reactant, it's going to be the same number, just with a negative sign. My concentration of the reactant is decreasing. Just do the math to figure out the rest of the table. My equilibrium concentration of the reactant, 0.015. The other product. Now I can get into my equilibrium expression. Up until this point, I don't want to even think about my equilibrium expression. There's no point to it. It's going to be a distraction. Once I've got my ICE table filled out, now I can actually get into writing my K expression. My two products. And my reactant. I don't need to do anything in terms of algebra because I'm looking for K, so I just plug in my values. that, I get a value of 0.0817. This is a K value that's less than 1. Therefore, I have a reactant favored. Equilibrium. I'm going to have more of my reactant concentration than I will of product. General. So we have this thing called reaction quotient. Yeah.
What's between KEQ and KC?
Kc is talking about concentration. KEQ is just the general equilibrium concentration. It's as long as you see capital K, you're talking about the exact same thing. Kc is just telling you using concentrations. The other version that you'll see is a Kp. That's using pressures. If all of your reactants products are in the gas phase, that you can use their partial pressures. And you'd set that up exactly the same way. Instead of concentration brackets, you would just use a P to indicate pressure. Otherwise, you treat it exactly the same. There's no difference between calculating a Kc or a Kp. Yep.
On the last slide, it said that reactants were favored, but the more concentration with the reactants was much smaller than the products.
Right, but that's based on what you're actually starting with concentration. It's relatively how it's shifting. It's less than 1, so the reaction's not going to go all the way to completion there's going to be a large fraction of reactants, relatively large fraction of reactants left behind. You don't want to get stuck on what the specific numbers are, because that's going to change depending on what numbers I actually use.
What does it mean favored then?
Favored is which way the reaction is generally going to go. It's going to, in this case, it's going to form some products, but you're going to have a significant fraction of your reactants left behind. You know, if the number was greater than 1, you'd maybe use up 95% of your reactants. In this case, you didn't use up nearly that much. You had a fraction left behind. You don't want to get stuck up in the specific numbers, just the general trend is what that's talking about. All right, this K value that we're talking about really is only useful when the reaction is at equilibrium. All right, so if you look at that first graph that I showed today, once you got to that plateau region, that's what the K value is good for, is doing calculations and understanding what's happening at that point. But what about when the reaction is still curved, when we're still progressing towards reaction? That's what this reaction quotient is useful for. Right? So this is, we can compare Q to K. Q gets set up and treated exactly like K. So when we write a reaction quotient, we're going to set it up just like we do with K. The only difference is we put a Q in there instead of a K. Nothing else changes. But when we compare Q and K to each other, we can get an idea of where the reaction is as far as progress. Right? Is the reaction shifted too far? Is there still too much reactant concentration, and therefore more products are going to form? Or have we pushed the reaction too far, and we have too high of a concentration of products, and the reaction is going to shift back and reform reactants? And that's what we're going to be able to tell by comparing Q and K. So, if my Q is less than K, doesn't matter what the values are. It could be greater than 1, they could be less than 1, but as long as Q is less than K in some shape or form, the reaction is going to form more products. It's going to go toward products. So if Q is less than K, our relative amount of reactants is too high. So the reaction is going to use up some of those reactants and form products. If Q is greater than K, it's going to move toward reactants. And I have my concentration of products is too high, and therefore it's going to shift back and reform more reactants. And then when Q equals K, we've reached equilibrium. another set of comparisons that you'll need to keep straight and know. So spend some time on these three factors as well in these two situations. When Q is less than K, Q is greater than K, and then Q equals K is pretty straightforward. So what is actually happening to the reaction when Q is less than K? The reaction is going in the typical direction, what we typically expect. Our reaction is going reactants to products. So the reaction is going to the right, like we typically see, like we typically write. If Q is greater than K, we're going to have the reverse reaction going on. Right? So we're going to go from right to left. We're going to read the equation in the reverse direction. We're going to go from products to reactants. And then when Q equals K, nothing's going to change. In terms of concentration, nothing changes. We're at equilibrium, so the concentration of reactants and products is stable, and that value is not going to change. All right, how are we doing? The clock's actually working. The clocks in here are notoriously bad. Just give me a shout if they're not, because I'm going by it.
What's the equation?
I'm doing that right now. It's gonna end up being the exact same as K. There's gonna be no difference. Let's see. So if I look at this, so determine if the reaction is at equilibrium. This is a typical use for the reaction quotient. My reaction, nitrogen gas and O2 is going to react to form 2NO. My equilibrium expression, K, is NO squared divided by N2 O2, and my K is given as 4.0 times 10 to the minus 4. That's my value for K. Is the system at equilibrium when my nitrogen concentration is 0.5 moles per liter, my oxygen concentration is 0.25 moles per liter, and my NO concentration is 4.2 times 10 to the minus 3 moles per liter. So I'm given, these are all equilibrium concentrations. So I don't need a nice table. So I'm going to set up and write my reaction quotient expression. Like I said, it's exactly the same as my K expression. NO squared N2 O2. Actually, coefficients, they become my exponents, keep those the same. Products over reactants, the same. Yeah, no difference. I can substitute my values in, because again, I'm given all equilibrium concentrations. So my NO concentration, 4.2 times 10 to the minus 3 squared. My concentration for nitrogen was 0.5. And for oxygen, 0.25. This solves down to 1.41 times 10 to the minus 4, and that equals Q. So right off the bat, I can see Q does not equal K. So I'm not at equilibrium. But if I compare, how is Q related to K? Is it less than or greater than K? 1 second. So my value for Q, that 1.41 times 10 to the minus 4, is that less than or greater than K? Less than. And this This will mean that the reaction is going to continue to produce more product. So I'm going to continue to increase my concentration of NO until I reach equilibrium. Yeah, question?
So you're saying that the bond Q is the same as bond K.
Yep.
Wouldn't that both mean that they're always the same?
No, not necessarily. It's all going to be concentration dependent. So the concentrations that I'm given here, I was given concentrations at a certain point in the reaction. This is what the concentrations are. Are those concentrations the same as equilibrium concentrations, or are they just some point during the curve portion of the graph?
So throughout every question, you would have to give us either a K or a Q if you want to solve for whichever.
Exactly. If the question is asking you to compare, or to tell me if the reaction was at equilibrium or not, I have to give you one or the other. Any other questions? So in this case, reactants must be converted to products to reach equilibrium. The reactants must be converted to products. So the reaction is going to move in the traditional forward direction in order for us to reach equilibrium. All right, a little bit more challenging exam type questions. The first one that we did is relatively straightforward. That's what I consider pretty much a gimme easy question on an exam. So something a little bit more difficult. We can go back to the reaction that we've kind of been talking about all the time. Hydrogen and iodine forming 2HI. My K for this is 55.64 at a temperature. We're not going to really worry what that temperature value is as long as it's staying constant. I don't care. So I have my initial concentrations are 2 moles per liter. Then I want to know what are my equilibrium concentrations for I2, H2, and HI. So I'm not given any kind of values for equilibrium. All I'm given are initial values. So I'll set up my ice table, my hydrogen, iodine, HI, bring down my coefficient, make sure that stays right in front of my face. That's going to become really important for this problem. So my initial values for hydrogen and iodine are both 2, and my product is 0. In this case, because I don't know what my equilibrium concentration is for any of my constituents, I can't determine what my change is. So I'm going to use a variable. I'm going to use x, and I'm going to lose some amount of hydrogen. Don't know what that is. I got to solve for that. Because I have a one-to-one relationship stoichiometrically between my reactants, I'm going to lose the same amount for iodine. And because I have a 2-to-1 ratio between reactants and products, I'm going to gain 2x for the HI. Again, the 2 is coming from the coefficient. Right? So at equilibrium, for a hydrogen, it's 2 minus x. Same for iodine. And HI is simply 2x. Okay. HI squared over H2 I2. And I know what my K is. told me what K is. I couldn't solve this if I didn't know K ahead of time. Then I would have two variables. That doesn't work so well. So I'd have to give you K. So now I can plug in my unknowns. So for HI, I have 2x. That's going to be squared. And for H2 is 2 minus x times 2 minus x. I just plug in my values there. Now we'll get into a little bit of math. I'm just going to pop over to the screen. So I'll write that again. My K is 55.64, and that equals 2x squared over 2 minus x times 2 minus x. Essentially, I'm going to rewrite the denominator. And simplify that as 2 minus x squared. Do that, that's pretty straightforward. So the simplest thing to do at this point is take the square root of everything. Alright? That'll simplify my x term. I work to there. Square root of 55.64 is 7.5. Again, I'm breaking this down slowly. Some people haven't done this kind of algebra for a little while. You'll get very good at this. We'll be doing this a lot. So we end up with 7.5. I'll bring over the denominator. That gives me 15 minus 7.5x equals 2x, or 15 equals 9.5x. And for x equals 1.58. This is not the answer. Keep in mind, this is not the end of the problem. I know my H2 concentration equals my I2 concentration, and that was 2 minus x, which equals 2 minus 1.58, which is 0.42 moles per liter. So that's my equilibrium concentration for hydrogen and iodine. That's 2/3 of the problem solved. My HI concentration was 2x, and that equals 3.16 moles per liter. So those are my answers. So don't make the mistake of just solving for x and say, hey, there we go, I'm done. Not quite. There's a little bit to be done after that. Not too much, just a little bit left.
So you need both of those to be answered.
Yeah, you need to know both those. The question is, what are the equilibrium concentrations of all three species? That's the question's asking. Yep.
Do you prefer that we do it this way, or do you mind if we do it like graphically?
However you want to do it is fine by me. There's multiple approaches. There's always multiple approaches to doing math in a lot of cases, I should say. However you want to do it, as long as you get to the correct answer and it makes sense to you, that's fine by me. Okay. This is what works for me. Right? And it tends to be the simplest approach. That's how I do it. But if you want to do something different, that's fine. Yeah. The product reaction? I give you the equation, and the way I write it, the reactions are traditionally always on the left, and the product is always on the right. It does go in both directions, but traditionally the way it's written, we consider the reactants on the left, the products on the right. Another question? Yes, no? Thought I saw her hand. All right. we're gonna get this one started. I'm not gonna be able to finish this problem today. I want to get this started. This is pretty much as difficult as the examples get. All right, so we want to work through this one. So a relatively simple equation: I2 going to 2 ID atoms. The K for this reaction is 3.76 times 10 to the minus 3. I know my initial concentration of I2 is 8.54 times 10 to the minus 3. I want to find my equilibrium concentrations for I2 as well as I. I'm asking the exact same question that I did previously. It's just giving me the setup, and the math that's involved ends up being quite a bit more complicated. Cringeworthy. Even. So I have I2 and 2I. I'm going to set this up exactly the same. My initial concentration for I2, 8.54 times 10 to the minus 3. The product is 0. I'm going to lose some amount, I don't know what, and I'm going to gain 2x, and again, from the coefficient. So at equilibrium, don't get sidetracked by what this number is, 8.54 times 10 to the minus 3, just because that's scientific notation. That's not any different than 2. Okay, so don't get sidetracked by that scientific notation. Don't think it makes this problem any more complicated. That's not the complication to this. All right. So K is going to be my product squared over I2. And that's equal to the 3.76 times 10 to the minus 3. So that's going to end up being 2x squared over 8.54 times 10 to the minus 3 minus x. And where the last problem, both my numerator and denominator were raised to the second power, I can take the square root of everything. This time I cannot. All right. So what I end up having to do is work this out. So I'll bring this down here. I end up with 3.76 times 10 to the minus 3 equals 4x squared. Don't forget to square that 2. All right. A lot of people will make that mistake and just write 2x squared. 8.54 times 10 to the minus 3 minus x. I'll bring the denominator over. We'll start to see where we're going to end up with this one. No place fun. So working through just some math to combine some of the terms together, I end up with 3.21 times 10 to the minus 5 minus 3.76 times 10 to the minus 3x equals 4x squared. Rearrange that slightly. 0 equals 4x squared plus 3.76 to the minus 3x minus 3.21 times 10 to the minus 5. And I have a quadratic equation. Oh, yeah. Grown-worthy, cringe-worthy. All right. I'm just going to throw up the equation very quickly, and I'll let you work through this, and we'll solve this again. Don't pack up yet. Make sure you get this in your notes. I want you to work through this over the weekend. 4x squared. Give me a couple minutes, guys. So this is my A term, my B term, and my C. So the equation for a quadratic is x negative b plus or minus square root b squared minus 4ac all over 2a. Right? So I'll let you work through that over the weekend, and we'll look at the solution on Monday. Have a good weekend, guys. Thank you.